is late night in Asia, evening here in Europe, and in the morning for those of you in the US. And we'll have 3 talks that cover the basically the ngEHT concept progression and the pathways. We'll have 3 speakers, which will give about 20 minutes each, including any questions on the spot. There's going to be question time later on in the in the discussion session, of course, for you as well. We'll start off with Garret Fitzpatrick, who's going to talk about systems engineering of the ngEHT. Go ahead, Garret.
All right, thank you, Anton. Let me just confirm you can see my screen.
Yes, we can.
All right, great. Well, hello, I'm Garret Fitzpatrick. I'm the project engineer for the ngEHT. I'm going to be talking about the systems engineering process and approach we're taking for the project. All right, my goals for this presentation are to give you a bit of an orientation on where we are in this project. We're at an early conceptual phase. I'll also talk about how we plan to get from where we are today to a fully developed and commissioned array that delivers transformational science, which is the goal of what we're trying to do here. I'll also talk about some of the major factors that are impacting the system architecture and design decisions. And then I'll talk about next steps. What do we want to get out of this week, and the next steps of the project from a systems engineering perspective. All right, I'll start here with the requirements flow down. We are here in the upper left portion of this diagram. As Shep and Michael mentioned, the focus of this week is on the science, on the themes, the questions, the observing requirements, and really trying to figure out what do we as a community want this array to go do. From there, we're going to be doing a lot of work to refine those use cases, to analyze them, to do a number of trade studies that figure out what is the best design of an array that delivers on this ambitious vision. There's a number of tools and documents and steps that we have that are proven from other industries and processes to follow. Ultimately, what we're trying to get to in the near term is the system reference design that fully describes the array architecture, the station architecture, and subsystem design. And after this talk, you're going to hear from Raymond, who's going to talk about the reference array. That's an example of array of what an ngEHT array could look like based on a lot of the site characterization modeling that he and the team are doing. So you'll hear about that soon. Our view in time, we are about 1/3 of the way through the current grant. This is an NSF mid-scale research infrastructure grant. The output of this grant is planned to be this implementation plan to build out the ngEHT array. In the meantime, between now and then, we have a number of milestones. Some of them are project driven, some of them are more NSF driven, all designed to try to get us closer to that implementation plan. As for what we're building, this is a product breakdown structure. It's a hierarchical view of the overall system, starting from the science and stakeholder requirements that drive the overall level 0 requirements of the array. This is a complex system of systems problem, so it's important to keep track of where we are in different levels. Level 1 is the array. It also includes the data transportation and processing, the array monitoring and control. Level 2 is station, and that's where we start talking about these new stations. There's also the existing stations and a number of the subsystems on data handling that also need to be considered, all the way down to level 3, which is a subsystem or instrumentation level, where we get into the specifications of the design of the instrumentation and infrastructure to get there. This is more of an internal view or interface view of the new ngEHT station. Again, it's early in the conceptual design. I think Shep mentioned a number of the requirements. We're looking at small dish antennas anywhere between 3 and 10 meters in diameter. We're looking at a simultaneous dual frequency observation at 230 and 345 gigahertz at least. We're going to be dealing with a lot more data So we're increasing and higher sensitivity. So we're increasing our bandwidth up to 256 gigabits per second. We're handling a lot more data now, and so up to 100 petabytes of data. And then other factors are around the monitoring and control. This operating mode is likely to be a lot more autonomous, a lot more remotely operated stations. So both at the local and the centralized array level, monitoring and control is a major factor. We're following a systems engineering process that is kind of tried and true in other industries. It follows progressive life cycles that go from the upfront early concept studies all the way to a fully verified and validated system. And it progresses through that, both on the subsystem level, but also on the system level. And that kind of process is something that we're following at various levels for various subsystems. The key here is to know how deep and how breadth, how wide to go in applying this process, so we can preserve some of the innovation, the rapid deployment, the quick creative design thinking, but also to follow a structured approach, because there's a lot of complexity with such an ambitious design. Other factors to consider is the time element. We've got near-term needs that are for each one of these subsystems that follow different technology development paths. We've got the near-term needs of the EHT, the existing sites. We'll be adding new sites, and then looking beyond into the later, longer-term view of the array. That means that their industry trends are going to shape up design decisions. We're going to have technical obsolescence factor in over time. So it just adds to the overall complexity, and something we need to consider upfront early at this stage in the design. Another way to think of it is, we have a number of existing EHT sites and a number of new sites. This adds complexity with interfaces, with compatibility. So we just need a structured approach that systematically looks at interfaces and compatibility over time. All right, so for development plan, this is kind of a high level view. I talked about the MSRI-1 being the focus on design and the completion of design work, both on the array and station level, also on subsystem level. Beyond that, we're looking at trying to get to a 2030 readiness of the full array. We're currently planning to do this in a 3-phase approach of adding various sites along the way. And that also includes a design iteration. We've got existing EHT sites. There's a lot of work to understand that aspect and to upgrade, but also to account for a continuous design loop, so that we're not locking in a design in 2023 for a full readiness level in 2030, which we know technology is going to adapt and change between now and then. I won't get into too much detail here, except to say that there is a more detailed view of this development plan, and there's a lot of opportunity for collaboration. There's a lot of moving parts here: the design of all the subsystems, the build out of these individual stations, and then the overall capabilities of the array. So we're going to absolutely need a lot of help, and this needs to be an international collaboration effort to go from where we are now to developing the first new stations, all the way through another design loop, and finally to the 2030 full array complete. Programmatic constraints, Shep touched on a number of these. I'll just reiterate a couple. Cost, of course, is a major factor. We're looking at a construction cost of around 140 million, with operating costs 13 million per year. We're early in this stage. We don't even have a full sites selected yet. So this is an early estimate. We have a number of cost modeling efforts that are currently underway. We want to get better at our cost estimating over the course of the next few years, which we will as we start to get progressively farther into the architecture decisions. looking at adding new sites starting around the 2026 timeframe with a full array in 2030. This is following an NSF process through the major facility guide, but it also does and will include a number of other funding sources. We're looking at roughly a 50-50 split between U.S. and non-U.S. sources, and again, it's going to take a big international effort. Early, the biggest areas are in the science working groups, which we'll talk about as we go throughout the week. Site coordination is going to be another factor, and instrument design opportunities to work together. And then the last point to point out here is the operational approach. The overall goals of this array is going to be a lot more similar to an experiment versus a facility. Our target is the event horizon, and that's going to drive a lot of the architecture decisions and narrow in some of the operational considerations as we go. All right, I'm going to spend just a couple minutes on the overall trade space. A trade space model, for what I'll walk through here is a way to visualize the full parameter space of all the design considerations. So on the one hand, you have things that you can affect in architecture decisions. You have constants that impact the overall the characteristics of a site. And on the right-hand side, you have the output, the attributes that determine the metrics you care about in performance, and then various cost metrics or program metrics that include cost and schedule and risk, complexity, things like that. I touched on a number of the requirements already, so I won't highlight too much here, except that we also want to consider what's driving the cost. We really want to be aware of those cost drivers. For us, of course, its location is a major factor. The environment we're going to be operating in, the environment we're going to be building in, access, infrastructure, logistics, things like that. Dish size is a major cost driver when it comes to construction cost. The operating mode, when we're going to be observing a lot more frequently to get this time variability, the movies of black holes, how that affects the operating mode is a major consideration and a factor on cost. There's a number of data transfer pathways, and then also the monitoring and control, which I mentioned. You can see the complexity only grows from there as we start thinking of all the different factors that impact the design. I'll mention that we're not starting from scratch. We have made some work on understanding the relative contribution of various site parameters and narrowing down the site list. We have done some concept work to understand what a higher frequency array is at 690 or above a terahertz, and we aren't going to be focusing on that, at least for the initial phases of ngEHT, but there's a number of open questions in the design space that we still need to handle. As far as constants go, this is mainly weather at the site and the overall characteristics of a site, dish pointing accuracy, proximity to local institutions, who's going to operate, who's going to, on-site staff, infrastructure access, things like that are constants into a model like this. As we start moving into the right-hand side, we look at what overall attributes, performance, both at the overall array level, the system performance, and then at the individual site. So signal to noise ratio, angular resolution, of course, total Fourier coverage is a major factor. There's a number of different metrics that we use to assess that and assess the goodness of a possible array. And Alex will talk a little bit about some of the work there and how we're doing that. And then, of course, as I mentioned, programs, so cost, schedule, complexity, and these are all factors we want to factor in at this point. So these are the various ways to look at the parameter space and how to manage the complexity kind of going forward. All right, so I just want to kind of end on this thought about next steps. We are going to be moving into a new phase of this project where we are going to start to make some key architecture decisions. We need to start kind of converging on science goals and priorities. That's why this is such an important meeting for the project to really build the community, to understand what is the priorities and what people are most excited about in doing in using this array for. We would like to come back as a community to assess trade-offs and look at requirements, within the next year. So in the meantime, we need the help. We need you to, get involved with the working groups, define, refine, prioritize these science goals. We're going, Shep mentioned, the ideas drive design, and that's really what we want to kind of emphasize here. We're going to be developing those science use cases and the associated technical requirements kind of over the course of the coming months. We need proposals for topics for science white papers as we start kind of building out the science book. And last point, we're not trying to reinvent the wheel. This is a number of projects have followed a similar path to go from science goals to requirements. I have an example here of the ngVLA, a recent example of understanding use cases from the community, translating those to discrete observations, and then deriving parameters from the community. This is a different project. We're going to be operating a little bit more narrow focus on the goals and kind of more of an experiment than a facility, but the process is something we'll follow fairly closely. And a number of other projects have kind of taken a similar path as this. All right, so that's really all I had planned here, and I think we have a few minutes for questions before we move to the next presentation. Is that right, Anton?
Yes, Garret, that's right. We have time for a few questions. I don't see any in the chat yet or any raised hands. So while people consider their question, maybe a question from me, Garret. How is there a sense of a scaling of a small, medium, on an optimum size of the ngEHT you'll plan with a view towards maybe funding caps or availability?
Size, you mean like number of sites?
Size and ambition. What is that, like scaling between what could you do with a minimum, an optimum, and a maximum of funding? Do you think in say a small, a medium, or like with the coffee that we've talked about, a small, tall, and grande version of this?
Yeah, good question. I don't want to steal a thunder. Alex's presentation is going to get into a little bit of where we draw the thresholds, and obviously there's a huge number of permutations of what we could go and build. What we want to emphasize is we want to build the best possible array given the funding schedule and overall community constraints that we have. So what's key to that is figuring out overall thresholds. What is the minimum number of sites and dish size and overall technical capability to meet our minimum success objectives. But at this stage, we still need to define some of those science goals. So it's we have a number of options of where we can go. I think it's a good thing to end up with have a few options in mind of what the array could be, depending on what other unknowns and uncertainties might pop up. But I think that's a little early. We're still kind of really trying to explore the trade space and figure out what are those drivers and where are the best sites.
Okay, thanks. There's a question for Marshall Eubanks. Marshall, hi. Do you want to say it out or should I read it? I'll read it. Does the project intend to construct new EHT-focused radio telescopes, or will it continue to use radio astronomy facilities constructed for multiple purposes?
Yeah, great question. It's a little bit of both. So I think a lot of the modeling has taken the assumption that most, if not all, of the existing EHT sites will be a part of it. Others, and Shep mentioned in his talk of the importance of an anchor station. So of course, anchor the whole premise of of an array of small dishes is kind of hinged around having a very high sensitive anchor station. So that's a key factor. We absolutely need to leverage the existing facilities, but then introduce this new operating mode of dedicated sites. There are some possibilities when we start thinking of entering a new country, of opening up a little bit of the design space for general purpose science applicability. And that's another reason why we want to be very clear about the overall system requirements, so we're clear about what we need to achieve.
Thank you. Move on to the next talk, and that's going to be by Lindy Blackburn. Lindy, are you around?
Yes, I'm here. Thank you, Anton.
Okay, good. Hi, Lindy. And Lindy is going to talk about data processing.
Okay. So hello, everyone. It's great to have so many people come here interested in the ngEHT. Trying to get rid of my Zoom. Sorry, 1 second. My Zoom participants window. So I'm Lindy Blackburn. I'm a radio astronomer at the Center for Astrophysics. I work largely on EHT calibration data reduction and also thinking about the data landscape for the ngEHT. This is going to be a pretty general talk with general considerations. It's based on a lot of work that many have done within the EHT collaboration and also this budding ngEHT group. So first I'd like to kind of emphasize how correlation is really central to the technique of VLBI. We're forming a computational telescope the size of the Earth. Our image structure is encoded in the spatial covariance of electric field at the Earth. And our correlator is digitally combining those signals from pairs of telescopes to form our virtual Earth-sized mirror. Now, the reason the data processing pipeline and pathway is interesting, besides the fact that the EHT and the ngEHT are projected to consume huge amounts of data, but also like radio telescopes, our instrument response is very complicated. So when we do VLBI, we have to deal with a large number of systematics. One of the biggest ones, of course, the Earth is round and moving, right? That imparts of velocity differences and geometric differences in the arrival times. But at these high frequencies, there are irregular delays from the troposphere, so sort of random path delays. We have different atmospheric receiver noise at all the sites, various electronics in path delays from different signal paths. Independent and imperfect clocks at all the stations. So in VLBI, we need independent clocks. We can't really distribute easily a coherent clock to all of the telescopes. And those change, and those have their independent characteristics. We have issues, or at least challenges with surface accuracy and pointing at high frequencies, possible post-digitization artifacts which crop up. And really none of these are known a priori with sufficient sensitivity that we need to be able to extract the science we want. So they have to be, in a sense, modeled and fitted, at least on a residual fashion after the fact. And all these systematics, for the most part, vary with time and frequency. So they are quite complicated, and there are a large number of parameters that describe the entire system. So for this reason, I mean, data processing is really the backbone for VLBI science. That's because the fundamental measurements are extracted computationally. And I just want to emphasize that proper modeling and ngEHT characterization are essential for a correct science interpretation. So here I just have a little cartoon that I made a while back to describe the EHT's data pathway, which is, ngEHT's pathway is going to model it pretty closely. We're recording and digitizing signals at our telescopes for the EHT. Maybe in 2021, we'll get something like 10 petabytes of raw data. Those are shipped to our central correlation facilities. The signals are combined. A priori, a delay model is applied, and the correlation coefficients are aggregated to some meaningful level, maybe about 10 terabytes of correlation output. There's a process of calibration and reduction. This is where we fit many of those residual systematics models. This is where quite often the largest order of magnitude reduction in data occurs, although not by far the largest volume of data. The correlator has to handle the largest input-output. And then finally, we can use those extracted measurements to try to fit our the sky model. And what's remarkable about this pathway is really the huge amount of data reduction that occurs. 12 orders of magnitude in something like going from the EHT data to the image of M87. And you can see just how simple our sky model is at the end of the day. It's a few pixels by a few pixels across. So this is characteristic of our high frequency VLBI. And part of the reason why we don't want to mess up the data through all of this calibration and reduction from our original data to the original source, to the final source model. So the ngEHT changes this a little bit. As Shep mentioned, we're thinking of doubling the number of sites and quadrupling the bandwidth over two separate frequencies. So in one case that may take our raw data per campaign to something like 80 or 100 petabytes. To reach these recording rates and to make the data handling manageable, it's very likely that we'll think of moving to solid state disk. Those are becoming cheaper and cheaper every year with respect to hard drives, although slowly. And also to increase the agility of the array, we would very much like to go to an electronic transfer mechanism. Of course, it's difficult considering the large bandwidths involved. The correlators, we have double the sites but quadruple the baselines. So the correlator output data, assuming the same aggregation, is increased by a factor of 4. So it's quite a large correlator output. The calibration, assuming everything is identical in terms of the complexity that needs to be left into the data at the calibration stage is maybe about 160 megabytes. But also keeping in mind the dimensionality of the problem increases as the number of stations and the frequency span increases. So that does increase the computational complexity quite a bit of calculating these calibration solutions. On the other hand, there is a sort of general principle that as we get more telescopes, the calibration problem does, in a sense, become easier because it does become better constrained. Now, one of the major changes in this pathway is at the end of the day, where we might be dealing with many or much more complicated source models than we did with the EHT. So this is just an example of that movie reconstruction of M87 jet. This is Andrew Chale's jet model of M87. It's a dynamical model, so in a sense, it may be much more complicated than the static images that have a very reduced field of view that we think we can reconstruct with the current EHT. Okay, so one reasonable question to ask is just why do we need such high bandwidths for the EHT and ngEHT? So this is an extended plot from what Shep showed, showing how the EHT is really enabled by the tracking of Moore's law for over a decade, and we're hoping to extend that to something like 2 decades now in the next generation. That's largely driven by our need for pretty extreme sensitivity in this difficult regime of millimeter radio to track the atmosphere at short time scales. So if we want to be able to anchor the station with some of our largest apertures in the array, we need a pretty high sensitivity. And if we're restricted to small dishes due to costs, we need to make up that sensitivity with bandwidth. So this is one of the reasons why we're going to 256 gigabits per second in total. The other one is a matter of fidelity. So Alex mentioned this issue with the limiting factors of dynamic range of the current EHT images. From our imaging paper from M87, we estimated a dynamic range in an image of about 10 to 1, and it was limited largely by our fractional gaps in UV coverage. So this is motivating Daniel Palumbo's metric from his 2019 paper. So you can see here there are fairly large gaps in the regions that are constrained really only by our priors. All right, this is field of view and smoothness, and then that uncertainty or that noise in the UV domain bleeds directly into our images and restricts the dynamic range. Now moving to ngEHT, the situation is similar. We still have some gaps in UV coverage. Of course, we don't have a final set of stations, so this isn't completely defined. But that does limit dynamic range. But I think you can see the coverage here. It's much more complete, and we have to start thinking about the actual RMS noise of the visibilities we do measure, right? That noise also bleeds into the image. So if we do want to maintain a dynamic range of something like 1,000 to 1, which is what we hope to to catch to be able to resolve this faint extended jet emission in M87, we'll need fairly low RMS noise on the visibilities we do measure, at least averaged over some relevant region in the UV domain. So that's also driving up our sensitivity requirements. And I just put this little demonstration on the bottom. As a general rule of thumb for a complex model like a movie, a wide field of view, dynamic range is often coverage limited. As our model becomes simpler, dynamic range is signal to noise limited. And many of our M87 or many of our ngEHT source models are going to fall somewhere in between these cases. So we'll have to worry both about sensitivity and coverage. So this is a picture on the left. We have some unique requirements for our ability to record and transport large amounts of data. On one hand, we need high bandwidth on-demand recording and playback. So obviously we need to record data live as it comes into the telescope at a high rate, currently 64 gigabits per second at DHT. But we also need to play it back quickly for correlation, right? So it doesn't take forever to correlate. So that's something like a hot storage requirement. But we also want to archive it for months, right? We might want to go back to our data later. So we need it to set, work as cold storage, and then we want to transport the data all around the world, to a central facility. Maybe we want to move it after the fact. So it also has to be flexible for transport. And that's led the community to create, semi-custom. Well, I guess the fourth requirement is that we want to do everything cheaply, right? So we don't want to cost a lot. So the community has developed these semi-custom solutions. These are banks of hard drives that we use in the EHT currently. Each one holds some, maybe 100 terabytes or so. And for the ngEHT, we may begin with something pretty similar. But hard disk speed and density, it does increase at a slow pace, and we can only replicate the system so many times before it just takes way too much space to achieve the bandwidths we need, and it becomes a burden for storage and transportation. So eventually, we'll have to, like the entire industry, really move to a commodity SSD storage. And if you look at the timeline of the ngEHT, this is probably going to be a few times more expensive than hard disks, but it comes with the benefits of extremely high density and bandwidth. So probably those benefits will outweigh the cost differential. So this is just an example. This is just one. The industry, there are many of these SSD volumes available commercially even now. So these are more or less commensurate in size. These banks of hard drives on the left and this SSD device on the right. Another thing that we're thinking about in sort of the long term for this kind of science is e-transfer of our data. This is routinely done at experiments where the rates are much lower and the sites are more accessible. For example, they've already all connected to high-speed internet backbones, which is not the case for the remote sites we have in mind. And there are a few ways you can do this, right? You can use ground fiber if you have it available. That's very nice. There are many developing satellite RF networks like Starlink, commercially available, which might provide rates of on the order of a gigabit per second, which is pretty good, not real time for our purposes, but maybe good enough to trickle a fraction of the data or trickle our data back slowly. And then finally, if we want to get approach the actual rates of ngEHT, we'll need something like a free space optical. So there's laser communications, maybe through a satellite relay like this LCRD experiment from NASA. So these are all being looked at. We wouldn't be developing our own networks of satellites, obviously. So we rely on the commercial development of these systems, and we use them as they become available. So looking at how it would be deployed, all of this data recording and transport pathway is probably deployed in something like a staged approach, and we explore e-transfer in parallel as it becomes practical. Okay, so a little bit about correlation on distributing resources. We also want to increase the speed of correlation. As Shep mentioned, we are increasing the data quite a bit, and the correlation can become a bottleneck. The VLBI correlation itself is inherently bursty, so using distributed resources can provide speed and efficiency benefits. And VLBI correlation itself, is trivially parallelizable, so it's very well suited for a number of small independent jobs in something like a cloud workflow model, something pioneered by a software haystack experiment called Corelex, and also this cloud concept, one of our summer students, Ajay Gill, pursued and wrote a paper up in 2019. So we're investigating the prospects for this sort of system. Where it's really deployed is a matter of where resource bottlenecks are. It could be on the commercial cloud, it could be the supercomputing center, or it could even be local distributed resources. It's also depending on what the resource constraints are. But the ultimate goal is to increase on-demand correlation throughput and minimize idle resources when the correlator is not operating. It's transport and storage still, of course, remains a major factor in this consideration. Now, one last thing about calibration and reduction. So I've defined here calibration as a modeling of the instrumental response, and reduction is averaging of data. And just an example of one of the things we have to deal with is atmospheric turbulence. And this is an example I gave on the bottom left here. This is a few minutes of live time of EHT data on a triangle of EHT baselines. And you see the phase in red, where a phase wrap is about 4 picoseconds. And you see the phase delay from atmospheric path differences varying over the course of this scan. So this is one of the systematics we need to solve for. The intrinsic source visibility is much simpler. You can see once those atmospheric corrections are corrected for or applied, we can then average down the data and extract only the single model visibility out of both an amplitude in blue and phase in red, or at least closure phase, the sum of these 3 phases in red across the triangle. But I did want to make one point, and that's correcting data is sort of inherently dangerous. And the reason is any appreciable model uncertainty really results in pretty complicated covariant errors, or I could say systematic errors that are pretty much impossible to quantify. This is one of the reasons I described calibration in this way, is modeling the instrumental response instead of correcting data. We have something like a classic data pipeline where we take our uncalibrated data and iteratively correct it with more and more fixes, maybe gathering in some a priori information or self-calibration to finally fit our images. But it's very difficult to track our error budget this way. And a more modern approach really uses something like Bayesian inference to build a joint model posterior of both our instrument and our sources. And just to be clear, everything I've personally done fits the classical data pipeline model, right? So I'm pointing fingers at myself here in a sense, but I do think we should try to think of this modern approach as we develop new software environments, and also modern approaches to our analysis. So I want to highlight a few talks. Tuesday's breakout session, Ilse von Bemmel will be talking about some of our software in the community. It really does extend beyond EHT and ngEHT itself. And then on Thursday, Katie Bauman is moderating a session on analysis and science extraction, which is also very relevant for this. Okay, so how am I on time, Anton?
About a minute and a half.
Okay, great. So this is my summary. So I hope I've given you a flavor for what's involved in the data pathway for the ngEHT. It'll really be a central feature of the array, driving the array capabilities. So I've highlighted these 3 aspects where we think the ngEHT will extend beyond the current capabilities of the EHT. So in dynamic range for images, being able to map images over time and make movies, and also spectrally over the course of the dual frequency range of the ngEHT. Our basic specifications, we have a double number of stations, quadrupling of bandwidth, resulting in about 60 petabytes per campaign, or it depends on the number of stations, maybe up to 100. And that's providing us a sensitivity to link smaller diameter dishes within the ngEHT. That's critical for the dynamic range we're targeting, and also critical for enabling this sort of snapshot coverage on Sag star that Alex demonstrated. And also it's important for the dual frequency operation we want for enabling this wide frequency span, which is necessary for testing of achromatic features in the black hole shadow, spectral mapping, measures of rotation measure, for example. And beyond those basic specifications, we have some next generation developments we'd like to pursue, things like agile recording and real-time transport, rapid correlation and joint calibration and modeling. And these will really be useful ultimately for full utilization of the array over time. So enable things like agile monitoring campaigns for AGN dynamics, and also maybe enable new observing modes. So opportunistic triggering, when we have, say, perfect weather across the entire array, which would be very rare, or target of opportunity triggering. And also as we develop increased sophistication of our calibration and analysis methods, these will really be useful ultimately for optimizing the signal to noise across the array, and also for, maybe most importantly, proper uncertainties and robustness in our scientific results. So thank you very much.
Thank you very much, Lindy. We're gonna have to end right here. And since we're up at exactly our time, I'd like to restrict. There's no obvious questions raised. I see no hands, no additional question. There was a comment in the chat, which you can read. And I think we can thank you and move on into the next question and answer session, which will include questions for Lindy. I hand off to Charles, I guess.
Okay, thank you, Anton. Can you hear me all right?
Yes, we can.
Okay. Welcome, everyone, again. I'm Charles Gammie. I'm at the University of Illinois. And we're starting the discussion session for the morning talks. And I think our non-local organizing committee has two people who are helping out. Nick and Daniel, you guys ready?
Yes.
Thanks. Okay, so this is an open discussion session, and you're welcome to bring up any issues that interest you. We had a number of talks this morning, and let me just bring up the chat here. And I'd just like to remind you of the morning talks with a single slide here. We had a welcome talk from Michael Johnson. Shep gave us an introduction to the ngEHT. Roger Blanford had an introductory science talk where he quite rightly pointed out that all is not quiet on the theory front, and that there is a tension between EHTC interpretations of M87 and the observed jet power. And then in the next session, we had three nice talks from Garret Fitzpatrick on the ngEHT development plan, Alex Raymond on reference array design or designs, and then Lindy Blackburn outlining the tremendous challenges that await ngEHT data analysis. So, so let me go to the questions and comments. Surely there are a lot of repressed questions now. So if you have them, please either raise your hand or type something in the chat.
So we have 4 raised hands right now, Charles, and I'll be keeping track of them as they appear.
Okay, thanks. Maybe I can start with Jens.
Yeah, thanks for the talks. And I have a question for Lindy and Garret, probably together. So you have talked about Garret has talked about the optimization of the UV plane, essentially. And Lindy now brings in this problem of the correlation and correlation requiring data transfer. And the data transfer will actually might determine how often we might be imaging. Is there any sense, do you have any idea how the data transfer will affect how often you will operate, and essentially, depending on how often you will be able to operate the array, that will influence what science you will be able to do. And that might be a bit different than the optimization in the UV domain that was discussed earlier. Can you comment a bit on that?
Garret, you want to go first?
I'll just mention that overall the operational cadence is a major factor. There's still a number of trades that need to be done, but one of the big factors is ALMA as an anchor station. If we're limited in the time that we get ALMA, how does that impact the overall ability to meet requirements operationally? And we're still at a stage where we're still assessing overall operations concept. But maybe I'll stop there. And Lindy, I know you've looked at this quite a bit on overall on the data side. Maybe you can add a little bit more detail.
Sure. Yeah, thanks for the question. I mean, this is one of the things I'd really like to learn more about during this week, is really what the kind of observing modes people are interested in, or most interested in. I think it's important to also keep in mind, if we hope to use such remote sites like Greenland Telescope or the summit of Greenland and South Pole, right? Our data transport strategy is going to have to pretty much work everywhere to be effective. So it's definitely going to limit the kinds of science we can do in many circumstances.
Okay, thank you.
Okay. Thanks, Ilse. Thanks, Lindy. So next hand up is Ilse. Ilse, please go ahead.
Yeah, thanks. My apologies first if this has been mentioned, because I dropped in halfway through. But I had a question for Lindy, actually, about the calibration of the atmospheric fluctuations. So from the way I understand, you would need some very bright point sources to calibrate these fast phase fluctuations. And ALMA can do that because they're basically looking all through the same sky. But if you're going to add smaller stations or even remoter stations to ngEHT, is anybody considering how you would then calibrate the atmosphere over these stations?
Sure, yeah, that's definitely consideration, right? The baseline sensitivity to some station needs to be sufficient to correct for the atmosphere. So that is a calculation we tried to do. We tried to calculate the baseline sensitivity between something like the LMT and a small dish, even in pretty poor weather, right? We were using a line of sight opacity of 0.6. And we assume that if we can do that at 230 gigahertz, we can bootstrap phase to 345 and lock the whole array together. But it is a limiting consideration of the array.
Okay. Yeah, thanks.
Okay, thanks, Ilse and Lindy. Next up, I see Rob, and then Raymond.
Yeah, thanks, Charles. So the last couple of hours have been my first introduction to ngEHT project. So perhaps this is something that's been discussed a lot previously. However, I got the impression from Shep's talk that the community were very receptive to the idea of ngEHT being a facility which could do many things. And I got a bit the contrary opinion from Garret's talk, where he repeated the point that this was very much going to be a focused experiment and not a facility. So perhaps Shep and or Garret could speak a bit more to that to give me a bit better idea of what's the goal here.
Yeah, can you guys hear me?
Yes.
Yeah, okay. Yeah, Rob, it's a very good point. We're looking at a couple of different models for deployment of the ngEHT. I think it's fair to say that the focus will be on the horizon scale science. The EHT, I think we all understand, benefited from its laser focus on one very high profile result. But we're seeing even there that the EHT can make inroads on AGN high resolution imaging of jet sources, for example, with the most recent result being from 3C279. So I think that the ngEHT will also have a second life or an alternate life. It'll moonlight, as they say, doing some AGN work, which is very high science payoff. At the same time, if we were to put, for example, 86 gigahertz receivers at the ngEHT sites, then we could interoperate with the longer wavelength arrays for certain periods of time, and in that way provide a service to the overall astronomy community. So we're looking at many different operational modes here. And of course, there is this cost curve that overlies everything, which it just turns out people do care about cost. So there will be a balance, but we think there is a way for us to dip our toe in both of these areas, a highly focused project with some moonlighting to do some good science.
Great, thank you.
Okay, I don't know if Garret wanted to comment as well.
No, I think Shep described it, really well. Overall, we're somewhere in between probably a fully focused experiment and a fully open facility. But as Shep mentioned, we're looking at a variety of operational models, and it will be driven by the science that we ultimately want to deliver.
Okay, thanks both. Now to Landon.
Thank you. Can you hear me?
Yes.
Thanks. I have a question to Roger Blanford, if he is still online. Are you, Roger?
Hi. Hi, Landon.
Okay. Okay, yeah, thank you.
Good to see you.
Yeah, nice to see you too. Thanks very much for a very inspiring introduction. And I have a question related to one of your bold statements, and quite provocative, I would say. You presented some arguments for the dominance of ejection rather than accretion of gas in AGN in the case of M87, or just suggested that. In your opinion, what would be a decisive, the most decisive discrimination between two models from the observational perspective? What would you like to see from an experiment which would say, okay, this is right, this is wrong?
Okay, I don't have a very good answer for you, and I wish I did, but I think the key might be polarization. One of the issues is that if you've got a lot of gas, then you've probably got a lot of Faraday rotation too, and I suspect that in a magnetospheric model, then you're probably not seeing the plane of polarization rotated in any serious way in the source region, whereas you will see that, particularly at slightly, obviously, lower frequencies in perhaps some of the other models. And so I would say that's probably the most prescriptive. And I would say the second thing is this general notion that all, obviously one goes to the limit in proposing a model, and then one has a sensible conversation how you've got somebody's attention. But if you take the view that essentially no gas accretes onto the M87 black hole, and I distinguish this very strongly from, say, a quasar like 3C279, where I think there's quite different physics going on. We say in M87, essentially no gas. The only gas you need is a tiny fraction of that which is supplied, necessary to make electrons and positrons. It may make electrical currents and charges, and that you can make in situ anyway. So if you take that limiting case, then all of that other gas has to be a hydromagnetic wind, and observing that hydromagnetic wind, particularly in conjunction with the VLBI observations of the outflowing jet, where the simplest inference, I think, all along has been that you're looking at a boundary layer. So that's telling you the inner edge of a hydromagnetic wind. And if you can find some observational manifestation of that in some of those sources, I think that will also be very prescriptive, especially if you can make it quantitative.
Thank you.
Okay, thanks everyone. Michael Janssen has a question in the Zoom chat asking how many active members should a healthy ngEHT collaboration have? Roughly how many FTEs would be needed to calibrate, reduce the data, publish results without producing a backlog of data? And I'm not sure who that's directed at, perhaps Shep, perhaps Lindy.
Yeah, I'll I'll take a first stab at it. It's a very perceptive question, and I want to point out that Michael Janssen is most qualified to ask that question because he has done some of the very, very hard work of calibrating the EHT data, so he knows better than anybody what's required. I think that in this design phase, we can operate with a smaller collaboration than we have currently with the EHT because that's an ongoing instrument. But in the fullness of time, I think the ngEHT will have to grow. And the key point there is that we want to accrete people who are actively participating. And as long as everyone is actively participating and contributing, then I think that we could make do with something on the order of 100 or 200 people, but we can, of course, flexibly expand as needed. I think that with the amount of data throughput that we have, and then that'll be gated by how fast we can process it. And hopefully with the cloud, we can process data in days or hours rather than weeks. Then the total throughput could be such that we'll need a much larger collaboration. So I think the answer is we'll have to see. A lot of it will depend on how fast we can process the data.
Lindy, do you want to comment on this?
Yeah, it's a tough question. I think the payoffs for bringing in people to actually look at the data very carefully and look at new ways to analyze it, calibrate both from the calibration side and source modeling side has huge payoffs, right? I think the more people, pretty much the better. Although we do need to be coordinated in those efforts, and we sort of have a compounding effect. I think trying to get the minimum number of people to kind of get the data through is not really going to provide the most scientific benefit. I think we want to look at it from many angles.
Okay. Thanks both. I see Avery Broderick's hand up, so go to him next.
Thanks, Charles. So I was going to just weigh in very briefly on this question of how many people, by noting that the ngEHT would necessarily need to have a handful of dedicated funding streams that would be able to hire and maintain a large group of people working specifically on task. And so that's a little bit different than the very ambitious and successful, but also much more distributed model of the EHT. So that's going to impact exactly this question of how many people we have working on what tasks. I also wanted to, maybe in the interest of discussion, throw out a question for Garret and company regarding, what has yet to be decided. And so very naively, I think of elements of the ngEHT living in three categories. The first is what still needs to be decided, and that's going to be driven by the science, beginning with what we talk about here this week. The second would be what could be changed if there was a great motivation to do so. So if there was a strong science case that something had to be different, what is possible to change in that way? And then last is what are those things that are cast in stone now that we really can't modify going forward? They're just part of the general concept of the project. So for example, I think the ngEHT is ground-based, right? So that would be one thing that seems to be cast in stone. But perhaps that's not true. And so I was wondering if Garret and others might want to comment on if that's the right number of bins. Is that the right way to think about it? And what would populate those bins if it is?
Yeah, maybe I'll just initially respond there on the fact that the parameter space, we have a finite amount of time before we get to an implementation plan. We have a window that we can affect the overall design of the architecture, but then we can't leave that window open forever, right? So The near term, that's kind of why this meeting is so important, is to what's open in your bin, Avery, of what's open. I think some of the science goals that are going to trickle down to a number of technical requirements. That's the biggest piece that does need to be pinned down. The operational mode, to the previous discussion about how often we're collecting data, that has big ramifications on overall the requirements of the array, the data handling, the monitoring and control. And so a lot of that can't be decided until we have more of a clear picture about the operations concept. So some of those have to stay open by necessity. Some of the things we need to move forward with in a design sense, just because we have a really good sense that it's going to be needed. 230 and 345 gigahertz simultaneous observation is a good example of that. We need to kind of move forward in those directions. We know we're going to need more bandwidth. So, designing for overall, more bandwidth, more data handling. Those are things we know about. Maybe I'll stop there and let others kind of chime in on this. There's a good amount that's still open, but we have kind of finite time before we have to start selecting the sites and moving it to further design stages.
Okay, any other comments on this?
Well, Charles, this is Shepka. Can you hear me?
Oh, yes.
Yeah. So I think Garret covered things pretty well. One thing that we thought about is you can decide where and when to make decisions. And one possibility is that we can design very carefully the stations. We can design very carefully the data processing, the data handling, and where we could expand in the future, where we could build in extensibility, would be to add new sites. So we might say, well, we can nail some things down, but then we could expand to 12, 13, maybe 14 new sites along a given template if we had put in the research to figure out what the most efficient type of station is. And we could think to build out in that way. So we can make some decisions, but then potentially leave some extensibility into the overall design.
Okay. If there are no other comments on that topic, then I'll go to Mohammed, who has his hand raised.
Oh, thanks, Charles. So my question, I don't know really who to direct it to, but Roger clearly explained that there is like basically two continuum mechanics description, which is GRMHD or force-free description, or you can also basically consider smaller scale plasma physics effects there. And so most of the library to produce these at least M87 images is based on GRMHD prescriptions. But what about the other continuum description, which is force-free or modeling from kind of reductionistic point of view? Is there any plans from the model side to make other libraries based on other prescription other than GRMHD, which is in some instances you can argue it's not really valid there?
I'm going to tell you what I'm. Can you hear me? Yeah. Okay. Yeah.
Yes,
I'm going to tell you what I'm aware of, which is mostly what I've been trying to do. I have no ambitions personally to create libraries in the spirit of the EHT MHD libraries, which are great and instructive, and I think they've been awfully good. But I am, I do have the tools to make occasional, I won't call them simulations, but at least make models with, I can do imaging and things like that. I know how to do that. And then I would say perhaps a more serious answer in the spirit of the project is that there are several groups of which I'm aware of, and I believe they'll come up later in the meeting, where, as I tried to illustrate on one slide, I think there are three things that you can doing these simulations, you know, if it turns out that there really is an accreting, you know, thick torus there supported by ion pressure, and, you know, it's conservative mostly, and the gas goes into the black hole and so on, which, you know, I certainly wouldn't rule that out. Then that sort of cries out firstly globally for MHD, for what comes out of the black hole, if that's significant, that cries out for, I think, force-free electrodynamics. And I have, you know, collaborated on proposals where people have tried to do that with MHD, and I think it's really rather problematic what is actually done in the simulations for what comes out of the jet. And then the third thing is the kinetic simulations, of which, you know, a lot of work has been done by, well, I'll show MPIfR et al., but there's other people who've been doing this as well, doing PIC codes and adapting them to general relativity. Now, those I think are very informative and instructive. The challenge, of course, is that, as I said, the larval radio of the particles you're talking about might be centimeters or something. Under these circumstances, there's a huge disparity of scale there. But, you know, there's a lot of effort going on in the simulation community to bridge that gap through hybrid simulation. So in even better ways to take what you learn from the kinetic simulations and feed it into the hydromagnetic simulations, including particle acceleration and radiative transfer. And I'm sort of pretty optimistic about whichever global model is right, that going well in the future.
Oh,
well, we
thanks.
have. Sorry, Charles.
So is there like a
over to Mohammed? Mohammed, I just want to answer.
easy estimate? Oh, sorry. Yeah.
Mohammed, please go ahead.
Yeah. So is there like a naive estimate to that one can make to estimate whether or where these kind of simulations can be most beneficial, like the hybrid approach? When do you like I understand that maybe like simulating the current sheet inside the ergo region is important. If a GR MHD, a GR BIC there would be important, but where else would it be important?
Okay. I mean, one of the, you know, the beauties of this sort of business is quite often you can do a good simulation for a totally wrong application and reuse it in another environment. And I'm seeing, you know, the same people are, you know, playing with things to understand pulsars, FRBs, black hole magnetospheres, galactic superluminals, and so on. And I think, you know, the hard work goes into developing the simulations tools. I don't do this. I mean, I'm sort of more a hanger-on for this business, but you know, the hard work goes into that. And I think people who do it understand fully well that, you know, their tools can be used in many different environments. And, you know, to sort of echo, you know, the Shep's answer to an earlier question, I hope and believe that, you know, ngEHT will in practice be spending a lot of its observing time looking at a whole range of unexpected sources, not just M87, exciting as it is.
Okay, thank you both.
Thanks.
So I guess I could make an editorial comment here, which is that there is something in between kinetic simulations and MHD, which is non-ideal MHD simulations, which attempt with some closure model to incorporate viscosity and heat conduction. And Michael is quite rightly pointing out in the chat that we have a couple of sessions on this tomorrow. Perhaps I could ask a final question of Roger, now that we're nearing the end of the session. So you pointed out that there's this tension between the jet power in M87 that you know, arises from the best astrophysical estimates from large scale data, and the jet power that arises from EHT collaborations and our group's estimate of jet power on small scales. and you proposed a model in which there's magnetic field that blows away the accreting material, I believe. So my question is, how can that be arranged? How do you prevent material from accreting onto the black hole? And if you do prevent material from accreting onto the black hole, how do you keep the field, a strong field on the hole?
Okay, obviously two excellent questions, Charles. I thank you. The first one is perhaps, you know, this does have, of course, precedent in models of rapidly spinning neutron stars and the so-called propeller mechanism of Ilarionov and Sonyaeva and many others long ago. So there you had a rapidly spinning sort of egg beater in the middle of an accretion disk, and the thought was that that would do something rather similar to this. What is different here, of course, is one doesn't have an excellent conductor called a neutron star in the middle of this. One has a rather imperfect conductor. And so the field has to be, to address your second point, the field has to be held in place against the threat of various instabilities and so on by a larger accretion disk. So, you know, the notion is that there's a rather large accretion rate at very large, you know, the radius in which the, you know, the HST observations are made, and that gradually gets driven off, that gas, until there's almost nothing left at what I would call the outer part of the clutch, which is where there's a sort of interface with what gas is left. And where that transition happens from being magnetically dominated to being gas dominated depends on, you know, the mass supply, and especially its history, because it, you know, really it could be quite a long way out, or it could be just, you know, a few gravitational radii. It really depends on the history, but it's basically going to be some boundary in this model that dependent on the, you know, on angular, mostly on angular momentum balance. Energy is part of the story, but it's mostly angular momentum. And that again depends on how much angular momentum is transmitted across the flux surfaces in this magnetic clutch. You know, in a simple stationary active symmetric model, it's none, but in one with instabilities like MRI and so on, it could be quite a lot, and that also is critical to determining, you know, where this would be.
Okay, thank you, Roger. And I think this comes to the end of the session, perhaps a minute late. We're on to the next